On previous slides, we were talking about polymer flooding in a single-layer homogeneous reservoir, where we had only one problem: high mobility factor causing viscous fingering during water flooding. We explained how increasing the viscosity of water by adding polymer to it can help decrease the mobility factor or mobility ratio and make the displacement front more stable. However, very few reservoirs are homogeneous. Many reservoirs are composed of more than one layer, and often these layers differ in permeability. Obviously, the displacing fluid, the oil recovery drive agent, will tend to propagate faster in the layer with the higher permeability. So the permeability difference between layers is another problem that slows down oil displacement. And we can overcome this problem by using polymer flooding. This slide provides a theoretical explanation of why, by increasing the viscosity of the polymer solution, we can make the velocity of polymer propagation in the less permeable layer equal to that in the high permeability layer. In other words, this slide explains why increasing the viscosity of the displacing fluid can result in more uniform propagation in both layers. Let's take a look at this figure, which was taken from this publication. It shows two layers with different permeabilities, both saturated with water. For simplicity, let's assume there is no oil present. In this case, we do not have any viscous fingering between polymer and water because the mobility of the polymer solution is lower than that of water. However, the penetration distance of the polymer in the upper layer is greater than in the lower layer. This is due to the permeability difference between the layers. The permeability of the upper layer is higher than that of the lower layer. Our goal now is to calculate the velocity of the polymer front in both the lower and upper layers. Let's start with the velocity of the polymer front in the lower, less permeable layer. By the way, polymer is shown in yellow and water is shown in blue. We will consider this distance L, which starts at the end of the polymer front in the lower layer and ends at the point adjacent to the end of the polymer front in the upper layer. This distance L. Over this distance, in the lower layer, only water is flowing. That is why we can use the simple Darcy law to calculate the velocity of fluid in this area. And obviously, this velocity V2 will be equal to the velocity of the polymer front in the lower layer. This is because by injecting polymer, we are pushing water out of the layer, and the water flow velocity will be equal to the velocity at which the polymer front moves in behind it. Next, we need to calculate the velocity of the polymer solution flowing over the same distance in the upper layer. We use the same Darcy law, but this time we divide by the resistance factor, which tells us how many times the mobility of the polymer solution is lower than that of water. By adding polymer to water, we increase its viscosity and reduce its mobility. So the resistance factor tells us how much we have reduced the mobility. Also, in both cases, we divide by porosity, as you can see in the equations. This is because the original Darcy law does not account for porosity, but we must consider porosity to find the real velocity of fluid in porous media, because fluids do not flow through the entire cross-sectional area of the rock. They only flow through open pores. That is why we divide by porosity to get the actual velocity. Okay, now we can find the ratio between V2 and V1, which gives us the ratio between the polymer solution velocities in both layers. Of course, the polymer front in the less permeable layer will never outrun the front in the higher permeability layer. However, we can make them equal. We can make the flow velocities of the polymer solution in both layers equal so they penetrate to the same distance. This will accelerate oil recovery. Here is what that ratio looks like. Obviously, we want this ratio to be equal to unity. To do that, we need to increase the resistance factor by adding more polymer to the water, which increases viscosity and further reduces mobility. The ratio becomes unity when the resistance factor is equal to this value, roughly equal to the permeability contrast between the layers, since porosity values usually do not differ that much. That is how we achieve a uniform displacement front in both layers. And this can significantly speed up oil recovery from layered reservoirs.